It's 1 minute past, so we'll get started. And I'd like to welcome everyone who's here today for our panel and discussion. I think it's going to be a great session. I'm Susie Titchener from Oak Ridge, and this is my colleague here on the screen, David Martin from Argonne, and we manage the ECP Industry Council together. And we're very lucky today that we also have with us Dave Kapczynski, who's going to be the moderator, and he's the chair of our ECP Industry Council. His day job is CIO of GE Research. I want to just give you a couple of logistical things and then we'll get started. I'm going to mute everyone, but you can unmute yourselves if needed. We just ask that you try to stay quiet throughout. And we're also going to ask that you put your questions in the chat because we don't have a whole lot of time today. We'll monitor the chat, and then when we get to the panel discussion at the end, we'll start to go through those too. And David and I will also put our emails at the end in the chat. If for some reason we don't get to your question, you can email it to us and we'll make sure we get it answered for you. And to our moderator and panelists, I'll come in at 1 minute before the end of your talk just to give you the high sign so you can wrap it up. And then at the top of the next session, I'll announce who the next person is. And right now, I think I'd like to turn it over to our moderator today, Dave Kapczynski. Dave?
Thank you, Susie and David, and thank you for having me. I just wanted to give a quick introduction today to everyone, a little bit of context, and then we'll turn it over to Andrew. But exascale capable.
Whoops, Dave, you got muted by mistake some way. So if you could unmute yourself.
Dave needs to be unmuted.
Yep, there we go.
Thank you.
So quick introduction and context. Exascale capable application development and software technologies are foundational elements of the exascale computing project. They're the vehicles of delivering our solutions. And then earlier this morning, I just took a quick quote from Dr. Harriet Kung from earlier. Delivering world-leading science and advancing the frontiers of science in support of our national challenges are the foundation of scientific discovery and innovation. That's what we're doing here with these areas. Today, we're going to explore how application development sets figures of merit, determines key performance parameters, calculates efficiency of our codes, and how that is executed within the Warp X and SEED projects as examples. The goal here is to improve our algorithms and code and fully leverage exascale technologies. So I'd like to introduce real quick our distinguished panelists today from ECP Application Development. The first will be Andrew Siegel from Argonne. Andrew is ECP's Director for Application Development, overseeing ECP's 24 application projects and 6 co-design centers. Next will be Jean-Luc Bay from Lawrence Berkeley. He leads ECP's Warp-X application development project. Warp-X is developing an exascale application for plasma accelerators that enables the exploration of outstanding questions in the physics of the transport and the acceleration of particle beams in long chains of plasma channels. And then third will be Sano Kolev from Lawrence Livermore. He leads ECP's Center for Efficient Exascale Discretization Co-Design Center, also known as SEED. It aims to develop the next generation of discretization software and algorithms necessary to enable a wide range of finite element applications to run efficiently on future hardware. And as a co-design center, SEED actively engages with ECP application and software technology projects, as well as ECP vendors. So that's a quick context and intro of everybody that will be on today's presentations, and then later on in the panel. So I'd like to turn it over to Andrew Siegel now, that will kick things off.
Okay, thanks, Dave. So I want to set the stage for Jean-Luc and Zanio by talking at a high level about how we measure performance for the applications and the exascale computing project, and a number of subtleties and challenges in doing this, and what's worked well and what hasn't, and kind of where we are. So let me first start with some high-level thoughts, and totally independent of how you measure performance, which I'll talk about on the next slide. I want to distinguish that from what you're trying to optimize, okay? And I'm going to tell you what we're trying to optimize in ECP and why. So just to give some examples, this is sort of brainstorming. And of course, these are issues that arise in different aspects of my work with different people, but they're not all directly relevant to ECP. So we can imagine optimizing price performance, right? So we're going to procure a system, and for a particular set of benchmarks or applications that we're targeting, we want to optimize by some measure of performance, the performance per dollar of the system, for example. We might be interested for various reasons in energy performance. It might be just because we have to pay a large power bill, or it might be because we're constrained by energy and we see a future to scaling up the architecture if the energy performance is very efficient. Could be all sorts of reasons, but we might be interested in performance per watt, although that opens up a lot of questions that are very deep, at least at a very high level. One could be motivated to think that way. You could just consider unconstrained performance, right? So you're just looking for the system that runs your suite of applications the fastest. You don't care what it costs. You just want to go as fast as you possibly can because there's some kind of return for being able to perform better, or to run faster, or to do larger problems. And the more you can do, the better. People talk about threshold performance, at least that's what I'll call it a lot. So oftentimes you want to be able to get to the next step in a certain set of simulations that you're doing. And you want the system that is sort of just good enough to get you to be able to execute that target problem. So you're sort of just trying to surpass a threshold, and anything beyond that, you might even consider maybe unnecessary. And then there is what I'll just call relative system performance. So there is sort of the ratio of how you perform, say, on some new computer you're buying compared to some old computer. And that's how we tend to think about it, as I'll mention in more detail in a minute, in ECP. And that's because the procurement of the system is done outside of the ECP project. So in other words, we take it, there was a large optimization problem, no doubt, solved when the exascale systems were being procured. But once those decisions were made, ECP was created now as consumers of those systems. And our goal is to run as efficiently on those systems as possible, right? And of course, we might study any of the other components of optimization that I have listed here, but it's not driving a decision we're making. The decision is made, and now we want to be optimal consumers of that particular architecture. And you can imagine other things here, like how much performance you gain versus the amount of time you spend on engineering software. So obviously, if you have a complex code base, there's a huge cost to any changes that you have to make in order to enable performance. And that could become a metric as well. So there's obviously a big space of interesting things to talk about here. And we have sort of in the end, a relatively narrow focus, but we consider all of these other things outside of the official project metrics. Okay, so that said, what about how do we define performance? Well, there are a number of ways to do that as well. And we have a particular way of doing it. And these are just decisions that we made at the beginning of the project. So you certainly could think about performance in terms of how efficiently a particular hardware resource is used. So you could just consider ratios of, say, floating point operations per second for floating point intensive workloads, which are typical, obviously, in scientific simulation. Or it could be system memory, use of memory bandwidth, or less typically, but it could be an IO intensive application. So you could think of doing better because you were able to perform more flops in the same amount of time, for example. We don't favor that because our goal is not really to perform flops. So I'll talk about that in a second, but that's one thing that people do. Another might be the time to solution, but for a very well-defined, predetermined set of algorithmic steps. And the reason I put it that way is because if you're going to enter, for example, into the a benchmark number for LinPack, you're not allowed to eliminate floating point operations because you have some kind of clever algorithmic way to get around them and produce the same answer, right? That would be considered cheating because, in a sense, you're measuring the capability of a number of the pieces of hardware simultaneously by how well it performs a very tightly constrained set of operations, right? So we're not doing that either. Okay, and this could be, there are obviously sparse linear system benchmarks. Now there are machine learning benchmarks, but if you want to do a comparison of machine capabilities, you have to tightly constrain what algorithmic innovations and exploration you're allowed to do. Going up to the right, of course, you could just think about how big a problem you could do, independent of the time to solution. But what we sort of chose early in ECP is what I'll call the scientific work rate. And that is how long it takes you to get to a solution of a certain accuracy for a target scientific problem. And implied in that is that it's not a toy problem. It is a problem of scientific interest in your community that would be considered some kind of beacon that you're reaching for, 6 or 7 years into the project. This includes algorithmic complexity terms. So for example, if you're doing more particles and the particles interact, then you include the extra n squared for the extra work that's being done. It's not linear in the number of particles, it's quadratic, for example, right? So that's all factored in. This can include very deep algorithmic changes. That's what's different about how we do it in ECP. So if you can do fewer floating point operations by reducing certain steps in the algorithm that aren't critical for the accuracy of the solution, or just reducing the complexity of the algorithm, then you get credit for that, right? Because you get to the solution of the same accuracy faster. You would not get credit if you were just counting floating point operations, for example. So that's a very important decision to credit people for algorithmic innovation. And that even includes up to approximate methods, right? And that's, of course, what's different about scientific simulation versus sort of traditional computer science, is that you have, the set of steps that you have to carry out isn't exactly clear. It depends on how much error you can tolerate. So if you can reduce the order of complexity and get almost as good an answer and demonstrate that, then you would do much better by this ECP metric of scientific work rate. Okay, so there's a lot that goes into it, but the important thing is the accuracy of the solution has to be part of the equation, right? Because if you get to the final solution faster and using a simpler method and your answer is not as good, then you should not receive credit for that. Okay, so that's sort of where we lie in ECP. And I'll tell you then formally how this works in the project is that every one of these projects has what's known as a key performance parameter. We call this the first key performance parameter, hence KPP1. And KPP1, which I said captures the scientific work rate, and it is a mixture of hardware-driven and algorithmic improvement. Oftentimes it's not separable. And when all of the projects entered ECP, they logged what is known as a baseline value of this figure of merit on the machines, which were nominally 10 to 20 petaflop machines that existed at the beginning of the project back in 2016, 2017. Okay, so the value of KPP1 at any point in the project is measured as the ratio of your best FOM. So it doesn't have to be on the exascale machine, that's the ultimate target. But at any point in the project, you can measure the FOM relative to the baseline FOM. Okay, and so there's a lot behind that story, and you'll get much more detail from Jean-Luc and Zanio. But at a very high level, that's what the strategy is. And each project then has a particular value of FOM that they of their FOM, which makes sense in their particular domain. And these had to be vetted and debated for the better part of 2 years before they were finally ratified at a certain stage in our project. And there's just a lot of nuance and a lot of things to debate. And my goal, together with the leadership team, was to define a consistent set of principles that all of the projects had to show that their formulation was consistent with, right? And so at some point we finally finalized these things. And so now I will give you an example of, for each of these projects, where in 2019 they were, for this KPP1 metric, on the Summit architecture, which is the sort of 100 petaflop. Now it's, I guess, the second fastest supercomputer in the world after the Fugaku system in Japan, but it was the fastest for a couple of cycles of the rankings. Summit supercomputer at Oak Ridge National Laboratory. And then we had them submit recently their updated best value. And the reason I show that is because I want to show the significant improvements that were made on those systems between 2019 and 2020. And what you'll also see is our bar of 50, which to meet our objective for the project, everybody has to surpass. We have sort of a minimum passing score, but everyone has to surpass this line to meet our sort of highest standard of success. 8 of the 11 on this particular system have surpassed it already. which is a huge surprise. It's something I would have never predicted at the beginning of the project. And so there's obviously a lot to discuss there that I'm not going to, but I also intended to show you the tremendous progress that everybody made. Not everybody. Some of the projects were focused on other things during the year, like portability, for example, in the case of this electronic structure project. But anyhow, I do want to make one point, which is that even though 8 of the 11 have been satisfied on this intermediate system between the starting system and the exascale system, this does not necessarily mean that they all have automatically succeeded on the exascale system. And that's because we're moving from all either CPUs or NVIDIA accelerated systems, so NVIDIA GPUs with CPUs, to exascale systems, which have completely new hardware. So although they're multi-GPU nodes, they're built on Intel and AMD GPUs, which is something we learned in the middle of the project, in which, although excellent Summit performance is very encouraging, there's a lot to learn about these systems. And a lot of it isn't actually the hardware. A lot of it is the entire software stack and its maturity. And so as the applications push to mature the software on these systems and to understand better how to optimize on them, we actually expect to see, in many cases, dips in performance relative to Summit before we see an ultimate surge, well past, hopefully, the values that you saw on the previous slide. And so I won't go into depth here, but if you just look at one particular application, and this is replica-based molecular dynamics. Okay, so this is looking at long time scale integration through something called the replica method. But the only point I want to make here is not that you see everything, but it's that this is the number you see right here is their starting value on the Summit architecture alone. And I asked this particular project to sort of log the steps that brought them a factor of 22 improvement. This is, again, from the first deployment on Summit up until where they are right now. And I asked them, is there one or two things that brought a significant step forward, or was it a lot of small things? And I had them log in detail every step of the way, the small optimizations they did, the small changes to their algorithm, how it was mapped to the GPUs, how they divvied up kernel launches. And it was really much more the steady, almost for a period, linear march up this performance curve by just lots of hard work with lots of people participating with different expertise. So it was literally people working at NVIDIA, people working at the leadership computing facilities in the DOE, and then people working on this project, some with expertise in physics, or in this case, the application sort of material simulation, and some with expertise in the either hardware or maybe different applied math aspects of HPC, right? So it's a really interesting story, but it goes to show you sort of how much work and how much collaboration and how many steps there are along the way, even if you just take a small window of time within the project.
Andrew, we're at 1 minute.
Good, because I'm on my last slide, which takes 1 minute.
Perfect.
Okay, so there are a lot of subtle questions in defining these FOMs. I couldn't get into much of them at all. Hopefully, we'll be able to dig deeper into them in the panel. But some of the interesting questions are, how do you give credit for algorithmic improvements? A lot happens over 7 years in a domain, okay? Domain scientists who are working in this field learn lots of think about new ways to do things, make discoveries about algorithmic improvements that they didn't think would yield so much benefit that do. So we want all of that to happen within the project. We don't want this to be a flop counting project, okay? But what I brought up earlier, specifying accuracy requirements. And then there are a lot of other issues, like we have lots of codes which are really couplings of what were traditionally independent codes. And how do we set a performance baseline for each of them independently, as well as the coupling? So there are all sorts of things that we've had to think about over the years. And as I say, the next 2 talks focus each on example projects that give deeper insight into these issues and how performance is tracked in new systems, sort of from a more interesting bottom-up perspective. But hopefully this sets some context that you'll find useful to understand those discussions a little better. So that's it for me. Thank you. And
thanks. Thank you, Andrew.
You're welcome.
If you'll stop sharing, and then Zanio, I think we'll have you go up next, and you'll do a share screen.
All
Andrew,
right.
thanks. We look forward to hearing more in the panel this afternoon, the discussion at the end.
All right. Can you see my screen and hear me well?
Yes.
All right. So I will continue Andrew's overview of how we measure performance generally in AD with an example from one of the AD projects, and particularly one of the co-design centers in the ECP, the Center for Efficient Exascale Discretizations, also known as SEED. So SEED is the central hub inside the ECP for PDE-based simulations on unstructured grids, for the tools that are used by many applications that need to perform such simulations in the application area. And we are particularly focused on next generation discretizations that use high order and spectral finite elements. So this is an example of a high order method that where inside an element you have a lot of resolution power. This is a 10th order basis function. And this means not just second order, but really arbitrary order discretizations on arbitrary order meshes, including unstructured adaptive mesh refinement. You have a lot of structure inside the element, but the general mesh is totally unstructured and could include adaptive mesh refinement as shown in this picture. Okay, this is what SEED is focused on, optimizing these methods and making them working with vendors and applications to make them work really well on exascale architectures. And some of our target applications include compressible flow, incompressible flow, climate, additive manufacturing, electromagnetics, and many more. We're always interested in working with new applications. And so as a central hub for this class of algorithms, one of our goals have been to develop standardized benchmarks that help us clearly understand the performance improvements we are getting from algorithmic developments, and also help us compare different implementations, different machines, and the progress we're making over time. That's the goal of this set of bake-off problems, also called BPs, also available on the SEED benchmark website here, that put together just the simplest kernels for higher order methods that capture application relevant information and provide meaningful optimization targets both for vendors and for our software technology partners. I've listed the first 6 of these BPs here. They're simple things like performing operations with a scalar, a vector mass, or Poisson matrix with a particular choice of quadrature order for different orders of the discretization. This is some of the illustrations of the intermediate vectors that are involved in that. And here you combine compute intensive and compute intensive operations with neighborhood communication, vector reduction. And the goal is to identify fastest implementations, to understand the scaling limits, and to collaborate. We have a paper where we compare several of the results from projects in this area, MFM, NEC 5000, and DIL2. All right, so here's how the results look like. When we plot this, we have the problem size per node on the x-axis and throughput, degrees of freedom per second on the y-axis. This is a scaling here of 10 to the 7th. And then different curves correspond to different orders. You can see that at first and second order, you're quite low, and you get higher throughput when you use higher order. You can do a simple performance model for this. If you just have one node, you only care about the maximum performance, the maximum throughput you get when you're doing a strong scaling problem. But when you have a parallel machine, you're willing to dial off of this. You may be willing to run at 80% efficiency. And n sub 0.8 is the problem size per node that allows you to run at this efficiency, 80% of the max. And then the time to solution, t sub 0.8, is actually the ratio of those two, problem size versus rate. That's the thing you care about in parallel. And if you introduce another parameter, we call it T0, this is kind of the serial portion of the algorithm. It corresponds to MPI communications, or in GPUs, it corresponds to the time for kernel launches. It turns out that this time at 80% efficiency is just 5 times T0. And so these 3 parameters, the maximum rate, the serial portion of the algorithm and the problem size at AD efficiency actually turn out to be connected by this formula. And what you want here is to increase Rmax, of course, but that's not by itself enough. You also need to decrease n sub 0.8 and decrease this serial portion. For example, decrease the kernel launch time for GPUs. Once you have these three numbers, you actually can devise a simple curve that kind of matches this quite well. This is an example from Mathematica. And so when we measure performance, we really care about not just the maximum performance we're getting, but also weighs this n sub 0.8. And so I want to show you three examples of that. This first example is for the first bake-off problem for CPU kernels with Ffts. And these are two of the kernels we have developed in our low-level library called libseed. This is the NaviX-based kernel and a kernel based on Intel's library libxSMM. As you can see here, we're getting the best performance for quite high orders, and at orders 1 or 2, the throughput is much lower, so it pays off to switch to next generation hardware methods. The maximums you're getting here are in hundreds of megadovs, maybe about 500 megadovs. The libxSMM performance is better. And the problem size at which you get 80% efficiency is in the 200,000 degrees of freedom. Now, things look very different for GPUs. I don't have two competing performances here. I have on kind of our initial kernel and our highly optimized CUDA Gen kernel, which is using, this is on V100. It's using code generation. This is done in MFM for BP3. The third, this is the Poisson bake-off problem. Again, the best performance here is for order 6, 7, 8, significantly higher than order 1. And the improvement that we've gotten here is from 0.6 gigadovs, so billions of degrees of freedom per second, to 2.6 gigadovs, so about more than 5 times, about 4 to 5 times improvement. But the important thing is that you need to have millions of degrees of freedom per GPU to get that to get reasonable performance in parallel. Okay, and let me close with now taking this to a full simulation on Summit and seeing what are the n sub 0.8 and t sub 0.8 numbers we get there. This is done with the NEC 5000 code. That is another participant in the seed project on a problem that's of relevance to the XSMR application. So it's an example of a flow in a nuclear reactor core with different rods here, different diameters. What they're comparing is run on Mira, which is a BGQ machine. On Mira, you can get away with 4,000 degrees of freedom per node. And the time you get per time step there is about 0.7 seconds. On Summit, yeah, go ahead.
1 minute, just a reminder. Okay.
Almost done. Almost done.
That's fine. That's fine.
On Summit, so this table here, we can use just a fraction of the GPUs. We need to use a lot of degrees of freedom per GPU, about 2 million. So that's in line with what we saw in the benchmarks. But the time step now is much smaller. So this is T sub 0.8. It's about 4 to 5 times faster, just using fractions of the GPUs. This is for strong scaling. We have also shown that get this approximate speed up for weak scaling too. And recently, this code was scaled to the full machine, more than 1 billion elements, really, really large problem. There is a lot of resources that we offer to applications. So this just scratched the surface. If you're interested to learn more about our team and how we can help you, please visit our website. And all the software that we develop is open source and available on GitHub. Thank you.
Awesome. Zanio, thank you very much. Jean-Luc, are you ready?
I am ready.
Awesome. Take it away.
Let me show my screen. All right. Okay. Good afternoon, everyone, and thanks for inviting me on this panel. So our code is WAPEX, and it's about exascale modeling of advanced particle accelerators. Let's see. Okay. Okay, so we model plasma accelerators, which is basically a way to accelerate particle beam, electron beam, or positron beams using plasma instead of standard cavities and is CERN, for example. And the reason is to develop particle accelerator that would be much smaller and hopefully much cheaper also than existing particle accelerator. And the stretch goal is to be able to model these futuristic accelerators in realistic time. So my keyboard is not connected. Okay, so the basic algorithm that we're using is very well known, is the electromagnetic particle in cell code. We push macroparticles at every time step using the Newton-Lorentz equations. The charge currents deposited on the grid, on which we then solve Maxwell's equations to the next time step. We then gather the electromagnetic force back on the particles from the grid, and we close the loop. So advanced algorithms are essential for us to reach our goal. We have to bridge many space and time scales to model these beams through these plasma accelerators, and just speed it up by going to the next generation exascale supercomputers is not enough. So there's a lot of development of algorithms. So one that has been used for a long time by us is to do the simulation in a Lorentz boosted frame, where thanks to relativistic contraction and dilation, the number of steps that we need to use is much smaller. In order to use higher accuracy, we're also basing our code on adaptive mesh refinement library with MRX. Just like the previous speaker, we also use arbitrary order FFT-based Maxwell solvers. For higher scalability, this FFT-based solver, we don't do with the FFT-based solver, we don't do the FFT on the entire domain, but do FFT on local subdomains with domain decomposition. We also take advantage of this spectral solver to use some algorithm that we've developed to control something called numerical Charge cost instability that occur in this relativistic simulation. And we also use lower dimensionality or reduced physics when available. So as far as the figure of merit is concerned, we are lucky because for the basic one, it can be very simple. So basically, we have in for the problem of interest, a laser that propagates from left to right here through a plasma, and the little black dots are electrons, macroparticles that have been displaced by the laser and create the wake to accelerate this electron beam that is in red here. And to very good approximation, the cost of the simulation is simply the number of grid cells plus the number of macroparticles, each of them scaled by some factor that takes into account the relative cost of each other. Now in practice, we usually have several particles per grid cell, and the number of macroparticles, the work of pushing macroparticles really dominate, and so the precise values of the factors is not very important, and multiplied by the number of time steps and divided by the work log time to do the simulation. Little caveat for the actual KPP runs, we don't run full simulation. That would require tens of thousands of time steps, but we run 1,000 time step, and we do preload a uniform plasma electron distribution, and we verify that the timing is unaffected, and it's a good measure of the actual work, a good representation. Boost from algorithms, as I mentioned, we have a lot of algorithm developments, like for example, mesh refinement, large time step is also valid, but as Andrew mentioned, and it is capped. So the boost from algorithm is capped as a value of 5 maximum. And also, as mentioned by Andrew, it's much more complicated than just doing this simple math here. There's more involved algorithm that can change numerical accuracy or stability. So they really need to have additional explanation, more analysis, convergence study, etc., to be able to do an apple-to-apple comparison and really have a valid accounting of this boost. Here's a table that shows the progress in FOM measurement over time. So the baseline was established with the previous version of the code named WARP. That was Fortran plus Python running on Core KNL for given grid size, run in about one hour and given FOM. And then already with the new version of the code WARPX, which at the time I think was still Fortran plus C++, we were already getting running the same problem. We're getting a nice speed up already of about 5. Then we moved from Fortran plus C++ to fully C++ to be able to run on GPUs. And there we got much more significant speed up, being able to first starting with smaller problem, then ramping up to larger and larger problem, and also having some good time speed up. So the FOM ratio, so the KPP1 then eventually jumped up to 132 with the last measurement that we did a couple of weeks ago. And so that's a combination of running larger problem and also running faster. And if we compare WARPX, the new code from Summit now compared to the full Core back in 2009, there's a very nice 30x improvement also. So this is without taking much credit yet for boost basically from advanced algorithms. The only advanced algorithm that we've been using in this KPP run so far is the ability to run in a boosted frame. But this was used already in the old code and was used for the baseline FOM. So we do not take any credit for this. We may take credit if we're able to run into, say, a higher boost that gives higher speed up. But we have not exercised that yet. These other advanced algorithms are still in development, are still being coupled all together so that we can run on the KPP, but we have not taken advantage of them yet. So there is room to grow here. Estimates is that there's further algorithmic improvements expected to boost FEM by a factor of a few in the next couple of years. And that will come in addition to further speed up of the code, just really by the raw speed up of the actual algorithm, really just pushing more particles on more grid cells in a shorter time. So we're already fairly quite happy with the result, but we see a lot of way to go. And I think my time is up. Yep, go ahead.
You have 1 minute.
Yes, and I'm basically going to my backup. So I can just quickly flash a great new result that we have. We have this new algorithm that enables us to take larger time steps, which we couldn't before. We were not able yet to run it on the FOM, to take reading on the KPP, but that's an example of algorithm development that we hope will push the KPP forward in a very near future. We'll stop here. Thank you.
Thank you, Jean-Luc. And we're going to move now to our panel discussion. And this will be moderated by Dave Kepczynski, the chair of our ECP Industry Council and CIO of GE Research. Dave, take it away.
All right, we're going to start off with just a question that we already had kind of preloaded. And then it looks like there's a lot of questions coming in through chat. So we'll grab one of those and work our way from there. But starting off with, maybe this one best goes to Andrew. You know, and it's a combined question because return on investment to industry is factoring in some other key indicators, including performance. So the question here is twofold. Do you factor in software costs to achieve performance? And in doing so, do you emphasize how much work, because people and man hours is cost, is required? And I'm thinking you do, but would like to hear from you on how you think of ROI in the context of, kind of achieving your KPIs on, the cost in doing so and the man hours involved.
Yeah, so I did make reference to that as a metric that we think about a lot when you're adopting a new programming model or running on new hardware. Thinking about the amount of time that is required and how much investment is required to be able to get whatever performance you're ultimately able to get. I don't think we typically think about return on investment. I think the reasoning is more that ultimately, if we decide that it's inevitable that to continue to make progress, the community has to move in this direction, then we think for what mission critical applications there are in the DOE, what investment is required to do it. And in this case, we knew there was a tremendous software investment that was going to be required. You can pretend like there isn't if, maybe if you adopt a more familiar programming model, but it's hidden even in that case. So I don't think you can get around the fact that there is going to be a tremendous amount of rethinking, algorithmic development, code refactoring. And that is the reason why ECP was designed as it was from the beginning, right? So this is sort of an unprecedented investment in developing applications at the same time that hardware is being developed and that a system software stack, in many cases, a new one is being developed, and all of the interactions that take place between them. So I think sort of in recognition of the fact that it was inevitable, there was a major investment made. And I think the reasoning was sort of the other way around, which is to continue to go forward, a lot of studying determined that the community has to kind of veer in this direction, that the old path, old straightforward path wasn't going to get you much further. So, I think that indirectly addresses that question, if not directly.
I think we were even thinking of that in the beginning of the session before anyone else joined, but industry thinks of return on investment, but it's really the same thought here. And if you replace the I with innovation, the investment is there, you're doing large returns on innovation. That's fantastic.
Yeah, I think that's nicely, succinctly put.
And then Sanyo and Jean-Luc, any thoughts on that one from your end and the projects that you're dealing with right now?
Well, okay, I mean, definitely in the thinking and the planning, there are a number of choices, for example, what algorithms to choose to solve the target problem. There's definitely the thinking of, how much investment and work is needed for a particular algorithm, and how much is it applicable not only for the targeted application, but beyond this, right? Because the target application is like kind of a moonshot, that something that we want to do that is valuable, but there's plenty of other planets that we could, things that we could visit, could go on Mars, or etc. So there's definitely some thinking here on the choice of what we do based on the maximizing the investment. And that was a very strong driver actually for WAPEX in particular on the choices of methods.
Great.
And maybe I can add that with the ECP, the transition to GPU programming was probably one of the hardest things from a software perspective that we had to do in our codes. And that was kind of a given, that was a constraint from the machines that were bought. And the question was, what innovation do we need to bring to the table, and how do we do that so the applications continue to run well on the next generation supercomputers?
Great. That almost leads into the next question that we had too, which is, I always put this one under the category of finding something new, something you didn't realize until you embarked on, all of the development work that had been done here. So the question here is, have you realized an area that just needed a total rewrite from the ground up instead of just refactoring? And as a result, did you achieve and exceed your original intent? Because I think the original plan here was, let's refactor where we can, but at some point on either your project or in a specific area of your application or software development, Did you realize that what was really needed was a rewrite ground up?
So I'm aware, I guess maybe I'll jump in because I'm aware of a bunch of such examples. And I think, one of the fundamental problems is that GPUs are naturally going to favor SIMD algorithms, and certain classes of algorithms are very naturally MIMD. I'll give an example, tracking neutrons. Okay, so tracking neutrons, since neutrons don't interact with each other, is something that can happen independently on each processing element, and they do not happen kind of in lockstep. So traditionally, if you were tracking billions of neutrons around some nuclear fuel or whatever, in some whatever medium that you're interested in, they would be done totally independently of each other. And you track each one from birth until absorption, totally independently out of lockstep. That just does not work on a GPU, whether you have one GPU or 6 per system. So the EXA-SMR team, who's looking at modeling small modular reactors, completely rewrote the algorithm. Completely rethought how it was done by switching to what's known as an event-based model. And I was skeptical that this would work, but the results have been tremendous. And the idea of an event-based model is that you process like interactions as batches because they undergo the same numerical operation. So you can do 16 or 32 of them at one time, but it requires doing the algorithm sort of one step at a time and doing a lot of sorting and merging as you process batches of neutrons. And so it's to me, it's just a completely different conception of the code, and one that you would never do on a CPU. So and there are other ones in that general class, right? Because being able to perform many operations, the same operation simultaneously upon multiple data elements, is obviously a key axis of performance on this type of systems.
So I can also add to that. Absolutely, the algorithms we've been developing in C for GPUs are very different than the algorithms for CPUs, and they're very GPU specific oriented. I somehow managed to go for a talk without showing the fundamental finite element decomposition, but we have, even on a very mathematical level, we split things in a way that is much more GPU friendly, because you try to minimize the memory transfer and the flops don't matter as much. And that drove actually some significant software changes, some codes that were written in Fortran, like NEC 5000. We actually developed a suite of mini apps that called lib polynomial internally, that then formed the foundation for NEC-RS, the next generation NEC 5000 code that's optimized for GPUs. And in MFM, we just developed a new version, and we refactored a lot of the internal kernels in a way that we did not anticipate in the beginning of this project to take advantage of GPUs. So that was definitely not the plan from the beginning. It was a lot of work that paid off tremendously. We're able to get great performance on GPUs now, and that's not for free. That's not just porting. That requires rethinking.
So very quickly for us, the main rewrite was our legacy Fortran core algorithms that we've moved to C++, using MRAC's portable writing. That was really our biggest rethinking. The other rethinking was, because compute was much faster, but message passing was still slower, than we had to change a little bit the way we operate and minimize the amount of memory that we use. So, for example, we had the field experience by each particle being stored for reuse. We now don't store it anymore. We go and look it up on the grid whenever needed, and that enables to do a lot more compute per GPU, basically, and reduce the footprint.
So let me do this really quick. David, is there a top question that we'd like to pull in from the chat right now?
Yeah, so there were a couple of questions around how you handle boot ups of kernels and how you handle that in the KPP calculations. I wondered if the panel could maybe address those. I can be more specific if it helps, but it's kind of the general question area there.
Okay, maybe can you be a little more specific? If
Sure. I mean, so from Tim Warburton, the current NVIDIA kernel first launch maybe
Oh.
200 microseconds, but once the cache subsequent launches, it may be only a few microseconds.
I think
he said, how much does, people were asking, how much do you care about the initial kernel launch time versus repeated launch times?
I think Tim was answering the question.
Oh, I guess he was answering Malcolm's question,
yeah.
right?
Yeah. This was a question about T0 from Arto. I believe that was answered.
Yeah, I guess Andrew was suggesting maybe we discuss some of these questions as a panel as well. So,
well, I'm not sure everybody read the answers, and there were some
Right.
good questions. So even just sort of repeating verbally what the answer was in the question would probably be helpful.
Yeah, so then one of the questions was, there some way to move to the left on the GPU initialization time, or is it a fundamental property of the systems?
So let me say what I meant by that, because I guess I just became an audience member at the moment. But this, these were kind of dramatic, what Zanio just showed, right? He was showing that the local problem size you need to get something close, I guess 80% is the way you think of it, 80% of the peak performance of the GPU is it was orders of magnitude, or at least one order of magnitude bigger on the GPU than on the CPU. And this has very deep implications for people solving real physics problems, because often you just want to run faster, which means spreading your problem out thinner, which means, and so I've seen him show this kind of stuff before, but I wasn't clear if there's something you can do about it, or if you just sort of accept it. And if you can do something, what can you do? And that was sort of the nature of my question.
Yeah, I kind of went a little bit quick through one of the slides where it relate that problem size to also this other parameter, T0. So there are 3 parameters, you pick 2 and you optimize 2. And you can think of pulling the problem size to be smaller, or you can think of removing minimizing T0. T0 on GPUs corresponds basically to everything that it's not just pure streaming and computation. So that's kernel launch, any type of transfer of data between the CPU and the GPU, right? That is not overlapped with purely parallel data streaming and computation. The kernel launch time, for example, on different types of GPUs is very different. And things could be done to improve that. And AMD actually has done things to improve that for their GPUs with different versions of ROCm, particularly with some of the newer ones. We've been working with them and providing feedback on that. But that's one way in which you can help. The other is, of course, to keep that in mind when you design chips. But I think that might be.
Well, I mean, how fundamentally part of the GPU architecture is it to require that much data to schedule efficiently? I mean, and another way to ask the question is, how much can reducing kernel launch time help? So how much of the problem is because of that versus things that are inherent to just about how GPUs
so in
work?
our model, if you reduce it 2 times and you have kind of an infinite machine where the MPI doesn't matter, you reduce your problem, you reduce your parallel runtime by 2.
Wow.
So it matters a lot.
Okay.
Good. And one just came in about the trade-offs between accuracy and performance. For example, using multi-pole methods for distributed FFTs.
I mean, there's always that discussion, and a lot of the projects are using approximate algorithms with lower complexity. And the question from a project metric standpoint becomes, what is a good enough answer in order to say that you have executed the problem? And it's just sort of a deep question that's specific in each case, but we have reduced order models all over the place. And, doing multi-pole FFTs, no, but not that I'm aware of, at least. Maybe Jean-Luc disagrees. I can't think of that particular example, but we have so many in computational chemistry and transport where the idea is to explore simplified models and make the argument that the answers are good within a certain approximation. So, I mean, it's too hard a question for me to address, I guess, spontaneously now, but the answer is yes.
So I think we'll stop now with questions from the chat. I think Dave has a few things to close up with here on the end.
Well, yeah, I think we're almost up on time, but one thought here, and it kind of goes to some of the questions that were in the chat. But if you were to leave everybody here that's on with either one lesson learned that is profound, we're past the midway point in ECP in all of the areas that have been under development. Either one major lesson learned or one major challenge that you're still working on that others can learn from, what would that be in your area? And I love this because today's context is in the context of projects that are currently in flight. And then Andrew, in your case, many projects that are currently in flight. So,
well, okay, so I was not expecting this question, which is good. So I'll talk off the top of my head. To me, among many surprises, I think the biggest one is that the notion of porting, as it is depicted, at least from the outside, maybe, is a bit of a fallacy, in the sense that there's really no such thing in, at least on the time scale of this project, and given the complexity of the codes and the changes in the hardware, there's no such thing as really just sort of rearranging loops and changing data structures. I mean, the things that people do to get performance on the new systems touch all aspects of what you consider simulation, all the way up to rethinking you know, how you do fundamental things like sparse linear algebra, even adopting different physical models, maybe, all the way down to things just like how you lay out data. And the other thing is that the people who use these systems are incredibly clever, and they'll find a way to get performance, but it will require this huge range of different ways of looking at the problem. And I think sometimes from the outside, people think, well, you just sort of tinkered with some loops and you kind of sped it up on this new machine. It looks nothing like that. I mean, the amount of research and innovation is sort of astounding. So that kind of surprised me. I don't know if I fully appreciated that.
I totally agree with that.
Go ahead. I just wanted to mention that what surprised me is how well and smooth the transition to GPU has been. For us, it has been fairly sudden because we were kind of following the CPU track, planning to jump on the GPU when we were all, you know, good at CPU. But there's been so much effort, you know, a lot of it done by ECP, right? To have this new paradigm, usually based on C++, to be able to write this code that run CPUs and GPUs, and that's been much smoother, and it was really nice speed up, much better than I was expecting, and that's really a great outcome.
Jean-Luc, I think we're going to quote you on that one today.
That's okay.
Fast and easy transition to GPU acceleration. Anything there, Sanio? It sounds like you were going to make a comment.
I totally agree with Andrew. I'm not sure. I totally agree with Jean-Luc. For us, GPUs were a bit challenging. I just wanted to say that one of the lessons learned is the importance of teamwork. We see it as a big team. It's about 30 people, and we could not have done it without working closely together. Projects like the ones that the ECP has put together are really, it's really important to get a lot of people and push each other, and then innovations really happen.
Okay, for my defense,
it looks like we're right on top of time.
Right, easy was the PI. No, just quickly. Easy is what the PI says. That's what I got. So the team will say, what do you mean by easy is fast?
And that was a great answer. You can't underestimate the teamwork and the organizational effort that's gone into what's happening here with ECP right now. So I just want to thank once again Susie and David for organizing this panel, along with Andrew Siegel and Sanio and Jean-Luc. Hopefully everybody really enjoyed the panel. And in the chat, hopefully everybody had seen this, all of the major contacts. If there were any chat questions that were unanswered, we're going to go through that one more time and see if we can make sure that we answer them. And then if there's anything in addition to this that we didn't get to today, please reach out to David and Susie, myself, and or the panelists. And we'd love to help answer any of those questions. So thanks again for the time today, and a great panel session.
Thank you to everyone.
Thank you.
By the way,
Thanks, everybody.
David also posted a link to a box folder where everyone's presentation is today. So you can go in and grab that too. And thank you to all of you, Andrew, David,